Last episode, our little cardpole agent learned by doing. It tried actions, got rewarded, and slowly invented a policy. Today, the network invents something even bolder. It invents pixels. We're in the generative corner of the pipeline now, still squarely in build and train, but with a twist. Instead of training one network to predict a label, we'll train networks to dream up data that never existed, digits that no human ever wrote, that nonetheless look completely real. So, what does generative actually mean? Every model we've built so far learned a mapping, image in, label out. A generative model learns something deeper, the shape of the data itself, the distribution. Once a model knows what handwritten digits tend to look like, the loops, the strokes, the wobble, it can do something new. It can sample, reach into that learned distribution and pull out a fresh example. The first way to do this is gloriously sneaky. It's called a GAN, a generative adversarial network. And the easiest way to picture it is a forger and a detective. The generator is the forger. It takes random noise and tries to paint a convincing fake digit. The discriminator is the detective. It looks at a digit and decides real or fake. Here's the beautiful part. They train against each other. Every time the detective gets better at spotting fakes, the forger is forced to make better fakes. And every time the forger improves, the detective has to sharpen its eye. It's an arms race, and the prize for us is a forger so good its fakes fool everyone. That's our digit generator. Mechanically, that arms race means 2 updates per step, not 1. We can't use the usual model, fit here. The 2 networks have opposing goals. So we write a custom train step with 2 separate gradient tapes. One watches the discriminator's loss and nudges its weights. The other watches the generator's loss and nudges its. 2 tapes, 2 optimizers, 1 tug of war. GANs are powerful, but they can be temperamental. That arms race can collapse. So let's meet a gentler cousin, the VAE, the variational autoencoder. It squeezes each digit down into a tiny handful of numbers, a latent code, and then reconstructs it. But the clever bit is that it forces that latent space to be smooth and continuous. Why does smoothness matter? Because a smooth latent space is one you can walk through, pick the code for a 3, pick the code for an 8, and slide along the line between them, and you'll watch the 3 morph frame by frame into an 8. Every point in between is a valid brand new digit. That's a latent space you can dial. There's one trick that makes a VAE trainable, and it has a great name, the reparameterization trick. The encoder outputs a mean and a variance, and we need to sample from that. But you can't backprop through a random draw, so we cheat elegantly. We sample a fixed standard noise, then scale and shift it by the mean and variance. Now the randomness is an input, not a step in the graph, and gradients flow straight through. And then there's the new royalty, diffusion, the engine behind the image generators everyone's talking about. The idea is almost childlike. Take a clean image and add a little noise, then a little more and more until it's pure static. Now train a network to undo one step of that, run it backwards step after step, and the network sculpts a real image out of noise. We'll show the idea today. It's a frontier worth its own series. Because here's the thing, a model that makes things up is only magic if it leaves the lab. Next, we ship it. Let's open 24generative.py, 9 short pages, the GAN, then the VAE, then a diffusion sketch. We'll walk it section by section, top to bottom, all TensorFlow and Keras. First, imports and data. We load mnist through Keras.datasets, keeping the labels around. We'll need them later to find a 3 and an 8. We scale the pixels to the range -1 to 1. That matches the tang. We'll put on the generator's output and wrap it in a tf.data dataset that shuffles and batches. Standard pipeline, nothing surprising yet. Now the generator, it takes a 100-dimensional noise vector, blows it up with a dense layer, reshapes it into a tiny 7x7 feature map, and then two conv2d transpose layers upsample it, 7 to 14 to 28, into a full digit, batch normalization and leaky ReLU between layers, tan H at the end, noise goes in, a 28 by 28 image comes out. The discriminator is the mirror image, a normal little CNN. Conv2d layers downsample the 28 by 28 image, leaky ReLU and dropout keep it honest, and a single dense unit outputs one logit. How real does this look? No sigmoid here. We'll let the loss function handle that with from logits. Here are the losses and the two optimizers. We use binary cross entropy from logits. The discriminator loss wants real images called real and fakes called fake, and we average those two terms, so a healthy value hovers near 0.7. The generator loss wants the discriminator to call its fakes real. That's literally the line cross entropy, one's fake output. Two Adam optimizers, one per network, both at a gentle learning rate. And this is the heart of it. The custom train step decorated with a tf.data function. We draw noise, and inside two gradient tapes we generate fakes, score real and fake through the discriminator, and compute both losses. Then each tape hands us gradients for its own network, and each optimizer applies them. Two tapes, two apply gradients calls. The whole arms race in 15 lines. The training loop just iterates epochs and batches, calling train step, and every 10 epochs it prints the two losses and saves a grid. Notice the numbers won't drive to zero like a classifier. In a healthy GAN, they hover and trade blows around their equilibrium. D loss near 0.7, G loss around 1. That's equilibrium, not failure. Next, we sample 16 fixed noise vectors, push them through the trained generator, rescale from -1 to 1 back to 0 to 1, and lay them out in a 4x4 grid with matplotlib. White background, no axes, those are 16 digits that never existed. Now the VAE compactly. The encoder maps an image to a mean and a log variance. The sample function is the reparameterization trick. Mean plus x half log varan times epsilon, where epsilon is standard noise. The decoder maps that latent code back to an image. The loss is two terms, reconstruction plus a KL term that pulls the latent space toward a smooth standard normal. And the payoff, the latent morph. We encode a 3 and an 8 to get their latent codes, then linearly interpolate 10 steps from one to the other, and decode each step. The figure shows a 3 smoothly becoming an 8. Last, a one-line conceptual panel for diffusion, a clean digit progressively noised, then denoised back, the forward and reverse process side by side. So, 3 ways to make things up. GANs forge through competition, VAEs sculpt a smooth space you can dial, and diffusion carves images out of noise. But a generator sitting in a script is a toy. Next episode, we crack open the machinery that makes all of this train: gradient tape, autodiff, and custom loops under the hood. Once you understand that, nothing in TensorFlow is a black box again. See you there.